Thanks, Jerry, and thanks for having me back. I appreciate it. Feels like only a few weeks ago we did this. Last time I joined you, I was still working with Wells Fargo, where I've been for about 18 years, and now I've transitioned and left that job and started working with RSM Partners here in the United States. And so I'm based out of Minneapolis, and I am running RSM Partners' operation here in America. So the presentation that I want to give today is a little bit about passwords and self-encrypting drives. And it's actually a presentation that I gave at Share last year and won a Best Presentation Award for. And the reason I'm giving it again today is because there's a lot of talk about encryption on the mainframe in the news. So with IBM's rollout of pervasive encryption this summer, included in that pervasive encryption, and it's obvious if you read the marketing material closely, obviously the big new rollout was data set encryption, but included in that idea of pervasive encryption are these other types of security features on the mainframe that also encrypt your data. So we're going to talk a little bit about passwords and how passwords are stored on the mainframe, and look a little bit at the evolution of that all the way up through RACF's newest password hashing encryption algorithm, which came out in 2014. We're going to look at DES and why, if you're still using that, you really shouldn't be at all, and DES's predecessor masking, just for completeness. And then we're going to switch gears and talk about self-encrypting drives. There's a lot of misinformation out there about self-encrypting drives, and I think it's prudent to discuss it just so people know what risks self-encrypting drives mitigate, and it might not be the risks you think they do. So like Jerry said, if you have questions during the presentation, type them in the Q&A box, and I'll answer them when I take a break. Or a breath, moreover, and afterwards we'll take audio questions if people have them. Just a little bit about RSM real quickly. So we do nothing but mainframe services and software. Primarily here in North America, we do security. So we do security assessments, which are like deep audits of your mainframe security posture. Pen testing, where we can work with your red team and do adversarial simulations against your mainframe, and software. We offer a number of software packages that we've built that would help administering your mainframe be easier, and maybe allow you to use some people who don't have mainframe experience to administer your mainframe. Just a little bit about me. I spent a couple decades in financial services. I am a tinkerer, hacker, nerd at heart who likes to work on things at the bits and bytes and instruction level. But I've also led large teams, and I know quite a bit about managing enterprise risk, and that is actually what kind of led me to building this presentation today. I've spoke at a number of different conferences, and I have probably what is an unhealthy need for things that go fast. It's just maybe where the mainframe fits in. Okay, so part one, we're going to talk about how the mainframe, and specifically RACF as your ESM. ECF2 and Top Secret work in a similar way, but the details under the covers are different. So the stuff that I'm talking about here is very much RACF centric. So in the beginning, there was not password encryption or hashing, there was password encoding. And to make this distinction, because encoding of passwords was necessarily reversible. There was and is a RACF masking program, the ITH-DX01, for years and years. Even after DES came along, people had this enabled, and we have actually found systems in our work not that long ago that had passwords in the RACF database that were encoded with the masking program, and you can still do that. You have to actually force the system to do it. It's no longer a default or even really that easy, but you can actually make it generate the masking algorithm. And the masking algorithm, just like I said, encodes the password. So it does some bit shifting, some logical ANDing, and exclusive ORing. There's no idea of assault or anything like that. So what you're meant to understand about this is having password storage in any means that is reversible is necessarily bad. Where we're going with this part of the presentation is to talk about what bad guys will do if they get hold of your RACF database or the passwords that are encrypted within them. And if you had a masking algorithm enabled, you basically just made their life super easy because they can just reverse your passwords and then use them. So just for completeness, when I was building this presentation a year or so ago, I looked all over to see if I could find the actual algorithm that is masking. And I couldn't find it, although I was able to find examples of what masked passwords look like, and I was able to tweak my system to generate masked passwords. So because I'm somewhat bullheaded and don't really like to take no for an answer, I just reverse engineered that algorithm by looking at it and ultimately came up with it. And this is it. So this is the extent of how the passwords were stored back when they used masking as the primary means of storing your passwords. And as you can see, it's pretty trivial. That's just a little bit about what it looks like at a binary level. So we move on past masking. It didn't take long for industry and government primarily to realize that we needed a better way to store data, not only passwords, but data in general. And so the U.S. government launched what was the encryption standard back in the 70s. And IBM came up with a standard that they referred to as Lucifer. Now, I don't know about you, but Lucifer is a fantastic name for an encryption algorithm. However, since it was for the data encryption standard that NIST put forward, it just got renamed as DES. But I think if they come up with another algorithm at some point, they should give it another great name like Lucifer. Ultimately, they adopted this algorithm as their encryption method for passwords in the 80s, and it was very secure for a period of time, for several years actually after that. And one thing worth noting that the mainframe stores passwords a little bit differently than do other systems. If you're at all familiar with, for instance, Linux and how Linux stores passwords, Linux actually stores passwords as a hash function of the password. So if your password is sunrise1, it actually stores the hash of that password, MD5 or SHA-256 version of that plain text as a hash. And the way that it decides whether or not you can log in when you try to log in, for instance on Linux, is you type in your password sunrise1, it hashes that password again, and then it compares the two hashes, the one that has stored and the one that you just typed, that was created based on the password you typed in, and if they match, you get in. The mainframe does it a little differently. The mainframe actually stores your plain text password, but it encrypts it. So what it does is it uses your password to generate a key, and then it uses that key along with the DES algorithm back in when DES was around, and if you still use DES today, to encrypt that username and your username and some other information, and stores that in the RACF database. And so the way that the mainframe is able to tell if your password is correct is basically generating a key and decrypting your user profile in the RACF database. And if your username is there, then it has then it worked correctly. So there's no hashes stored, there's no password stored. I think I misspoke just a minute ago and said that it actually stores the plain text password. It stores your user ID and some other information. It doesn't store the plain text password or any derivative of the plain text password. It only just encrypts this blob that includes your user ID and some other stuff. So it's actually a pretty good practice, and it's a little bit different than how other systems work. However, entered into the 90s, and computing power became more and more available and cheaper and stronger, and criticisms for DES came up pretty quickly because of its relatively small key size. So a 56-bit key size is not a very large key, right? That's 7 bytes in a key. If you compare that to AES, you can see there the difference in this key size is exponential. And so what happens is it actually becomes fairly, in the 90s, I wouldn't say trivial, but possible or plausible to do a brute force attack against that key. So if you remember, if I said the process for saving your profile in the RACF database involves taking your password, creating a key out of it, and then using that key to encrypt some information. What people started doing in the 90s is actually trying to basically just brute force that key, not your password, but that key. And what they were able to do back in the late 90s is RSA, the company RSA, issued a DES challenge, and they were able to do it in 39 days. They were able to brute force DES key in 39 days. EFF, the Electronic Frontier Foundation, created a large computer that cost them only $250,000, which back in the 90s, late 90s, was a lot of money, but it generated it was a pretty big computer called Deep Crack, and that actually cut the time down to 55 hours. So now we consider DES thoroughly broken at that point, because 55 hours and $250,000, depending on who your adversary is, if it's a government or a nation state, is trivial. And then a collaboration sometime later almost at the end of the 90s or early 2000s, was able to brute force a DES key, a known DES key, in 22 hours. So at this point, in the late 90s, DES is thoroughly debunked and broken. A couple of things that happened, you might be thinking to yourself, well, it was broken, but what other alternatives were there? Well, there were actually some alternatives that were created even in the 90s, and you'll see where I'm going with this shortly, because it actually took IBM another 15 years from the year 2000, from the year 1999, to create an algorithm that was using all of the technology and things that were available to the rest of the industry back in the late 90s. Sometime around the late 90s, they came up with a way of parallelizing brute forcing DES called bit slice DES, and it sped the algorithm up tremendously. And as you'll learn as we talk about this a little bit further when I start talking about password cracking or password brute forcing, a fast password hashing algorithm is bad. I'll say that again. So an algorithm that stores your password, that hashes your password or encrypts your password, the speed of that algorithm is inversely proportional to the security of that algorithm. The faster the algorithm, the less secure it is. And we'll talk about why that is in just a minute. But when you hear people talking about cracking passwords, you might have heard of programs called John the Ripper or Hashcat. They're not actually cracking the password in terms of the actual algorithm. What they're doing is more of a brute force. They're generating possible password candidates at a rapid rate, running them through the same algorithm that stores your password on the system, but they're doing it offline. They're doing it offline on computers with large CPUs or GPUs, which we'll get to in a second, and they're doing multiple tens, hundred thousands, millions, maybe even billions of hashes tries per second. So you can see at that rate, it's only just a matter of time before they generate enough passwords that they will find one that will match the hash that's stored or be able to decrypt the blob that's stored. So sometime in the 80s, we figured out that if we iterate hashes, that we can slow this down. And what that means is instead of just taking one hash of your password and storing the outcome of that hash, what we'll do is iterate that. So we'll take your password, hash it or encrypt it, and then we'll take the result of that, hash it or encrypt it, and take the result of that and hash it and encrypt it, and do this 100 or 1,000 times. And what that serves to do is slow down the algorithm, right? Computationally, You may not notice it as a user sitting in front of the computer, but computationally, in terms of CPU cycles, it takes longer. And why is that good? That's good because if I get your RACF database offline and put it on my password cracker, the slower that algorithm is, the longer it's going to take me to find potential password candidates. Sometime 2001 was when the U.S. government adopted Rheindoll as the advanced encryption standard, or as we know it now, AES. So both being symmetric ciphers, DES and AES, 2001 was when it was adopted as a standard by NIST, and now is considered the de facto standard for just about everything today that uses a symmetric cipher, including IBM's newest RACF algorithm. So we can't really talk about password cracking and brute forcing until we talk about key space for a minute. So when I talk about key space, what I'm referring to are the potential characters that you can use to generate a key, or in this case, a password. So in the early days of RACF, the key space consisted of only uppercase alphabet characters, 10 digits, 0 through 9, and 3 special characters. So that's only 39 possible candidate characters with a maximum length of 8. If you do the math on that, that actually doesn't generate very many possible passwords in total, assuming that your possible passwords are 8 long and not 7, 6, 5, or 4, and that you throw out obvious ones or known bad passwords, if you will. In 2005, RACF introduced the option for mixed case, so that added another 26 candidates to the password pool in terms of adding lowercase characters. So now you've got upper, lower digits, and 3 specials. And then in 2007, they introduced the idea of a passphrase. And I'll just say a minute about a passphrase. If you're not using passphrases, highly recommend you do. You don't have to have a super secure passphrase if it's long enough. So in other words, length in terms of your password or passphrase rules the day. A 26-character passphrase that's all A's and 1 B somewhere in the middle is a super secure password from a brute forcing point of view. So I tell organizations when I talk to them, I said, you should turn on passphrases if you can and set the minimum length to like 16 or 18 or 20, and then I usually get some kind of groan in return, like, oh, how am I going to remember an 18-character passphrase? And I say, well, you know, what you're really looking at here is just something you can remember. It could be a line from a song or something like, every day I go home and open a Coke. Like, that sentence is a good passphrase. You put a period at the end of it, and some punctuation in there. That's a very good passphrase. And then I tell organizations, once you've done that, you don't need to make people change them all that often. In fact, NIST just changed its recommendations on password change frequency, because the more often you make people change their passwords, the more likely they are to come up with insecure passwords. So it becomes a case of using something like Sunrise 1, and then Sunrise 2, and then Sunrise 3, and so on. It's actually very difficult to come up with an 8-character password that meets the, you know, upper, lower digits and a special, and change it every 30 days. You're better off having people having longer passwords or passphrases and have them changing it far less frequently, maybe every 3 months or 6 months. So back to our cracking. And one more thing I'll say about that is most of the organizations we see now have mixed case turned on. Very few of them use passphrases, and a lot of them still have the original DES algorithm turned on. So back to cracking, John the Ripper came out in the late 90s and could run DES brute forces at about 3,000 candidates per second. And sometime in the, it was 2010 or 2013, the RACF algorithm was added to John the Ripper, so that if I get the RACF database offline, I can have, I can just point John at it and let it go to town, brute forcing the passwords in that database. And I don't need to have them all, right? That's the other thing. If I get a RACF database that has, say, 50,000 users in it, well, there's probably 100 or 200 or 300 or maybe even 1,000 users in there that would be juicy enough to me that if I got one of their passwords, I wouldn't need to really go on. Unless I get a system administrator or a DBA or a security administrator or a storage administrator, it's pretty much game over. So I don't have to crack all the passwords. RACF Snow is worth honorable mention here. Nigel Pentland created a standalone C-based and very optimized RACF password cracker. The industry starts really leaving RACF and its password algorithm behind into the 2000s. This idea of memory hard algorithms popped up. Remember earlier I said that fast password encryption or hashing algorithms are bad. They are less secure. Fast algorithms are great if you're browsing the web, but if you're storing a password on a system, you want that algorithm to be intentionally slow. So PBK-DF2 came out in 2000, which basically hashed passwords and with a tweakable iteration count. And that allowed for the operating system to increase the number of times a password gets hashed. As CPUs become faster, you can increase that number. So the next generation of CPUs come out, maybe instead of iterating that password 1,000 times and storing it, you do it now 10,000 times or 100,000 times. Current implementations are well north of 100,000. In late 2009, Colin Percival released a algorithm called Encrypting, and it took it one step further. Instead of being just intentionally CPU hard, it actually was intentionally memory hard. And so what that meant was it basically made it so that the algorithm could not be parallelized. You had to sequentially do these operations, and it took up a sizable amount of memory. So you not only do you have the iterated time, but you also have the time that it takes the system to write this data to memory and then read this data back from memory. So those become exceptionally good algorithms and are used now, like Scrypt and Bcrypt are used in various different password hashing mechanisms. But still, we haven't gotten any update from RACF. And then sometime in the mid-2000s, in 2007, someone invented a means of using the vector math on GPUs. So GPUs, the graphics cards in your computers, what they're designed for, if you think of running a really intensive video game on your game console or on your computer, what those graphics chips on those cards do really well is vector math, meaning that they take wide arrays of numbers and can do operations on the entire array as one operation. And so what those GPUs allowed password cracking to do was massively parallelize operations against brute forcing password algorithms. And this now made it orders of magnitude faster. And we'll see in a couple of slides down the road just how much faster this made it. When it comes to DES, the answer here is not good at all. So I took a friend of mine who works for a pen testing company that's got a GPU rig strictly based for password cracking, probably $10,000 worth of a computer here. You can build one at home for $1,000 that will perform very well, but I wanted to kind of see what we could do with a really good rig. So this thing's got 6 GPUs, takes quite a bit of power. Today's model costs about 10 grand. At the time, they spent about 3 grand on it. But it will crack DES at about 11.9 billion hashes per second. So what that means is if I get your RACF database and I put it on this baby, I can generate almost 12 billion potential password candidates every second. So at that rate, within a minute, maybe not even a minute, I'll have enough passwords cracked on your system, assuming that you're not using passphrases, assuming you don't have two-factor enabled. I'll have enough passwords off of your system to be able to get something useful. So here's an idea, just as an example. This is basically the time to brute force every possible password candidate, depending on what your RACF password settings are. So for instance, if you have the maximum settings, so you have 8 characters, but you're using upper, lower digits, and all the new special characters that are available, I can brute force every conceivable password in a week. All the way down to if you only have the original set, which was just upper digits and special, in 37 minutes. So in 37 minutes, I can generate every conceivable password if you don't have any of those other RACF options turned on. Now that's only brute forcing, and when I say that, that means that the system is actually generating the possible password candidates. So it's doing like A, etc. When most people aren't setting their passwords to those kinds of things, they're using words or permutations of words. So there are existing today lists of literally millions, hundreds of millions of passwords that have been gathered from different breaches throughout the years. So when somebody dumps on the internet a bunch of usernames and passwords because they hacked into some company and downloaded their usernames and passwords, there are people out there that are taking those passwords, not the usernames or any identifiable information, but just the passwords, and adding them to these massive lists. So it actually takes considerably less longer than these times on the screen if you use password lists, which everyone does. All right, so 2014. 2014, IBM releases KDS AES. So this algorithm does everything right. And I tell people, if you're not using it, this is a really, really fairly easy thing to turn on and test. It's backward compatible with DES. You don't have to do a lot of work to enable this. It will use some more CPU. It's designed to use CPU, so you may want to test that. But you can actually just, if you have a test system, you can actually just flip it on. And the next time the user changes his password or her password, it will start using the new algorithm. You can go through and force people to change their passwords or convert their passwords, or you can just wait until they change their password normally. But essentially what it does is it becomes it's an algorithm that now generates this key that uses to encrypt your data, and instead of using DES to encrypt your data, it's using AES. Now AES is still a really fast algorithm, but the part of this that's slow is this key derivation function. The key derivation function actually uses hundreds of thousands of iterations before it generates the key that actually encrypts your data. There's a couple of parameters that IBM has included with this to make it, you can see they get an eye towards making this future-proof. They don't support these parameters yet, but they are documented. There's tunable parameters that included in this algorithm that basically let you increase the number of iterations it uses to store password either linearly or exponentially. Like I said, you can convert the passwords if you want using pwconvert, but it absolutely slows down the speed with which people can brute force passwords, and I've got a comparison chart here coming up. But essentially what it does, by using thousands and thousands of iterations, it slows down considerably the amount of time that it takes to generate an encrypted password. So I did do a little bit of research into this just to kind of see how future-proof this was, and it's pretty impressive. Now, I have to say, per IBM and per me as well, this isn't supported. You shouldn't do this. Anybody who's ever used RACF block update knows like you shouldn't do that either. And so I don't recommend anybody doing this. Don't try this at home. Don't try this on your test system. You can really screw up your RACF database. But I did this just to see some idea of what I could do in terms of slowing this thing down. So there's also, along with the KDS AES algorithm, there's also a new database format. Because the encrypted password information is stored is a little bit bigger, and so it does require you to apply a new database template to your RACF database. So some of the information stored here is, like I said earlier, there's a repetition count. There's a memory factor, which is like an exponential multiplier of the repetition count. This PWDX is actually a kind of an eye catcher that lets you know that this is the password algorithm in use. A couple of the variations here, if you're using passwords with it or if you're using passphrases with the new algorithm, you can see that in the RACF database as well. Using passphrases with this new algorithm is I would just say, nearly bulletproof way to store your passwords. If you're using passphrases and this new algorithm, there's almost zero chance that someone with today's technology is going to be able to brute force those. So even if they get a copy of your RACF database offline and you're using a passphrase of sufficient length and this new algorithm, I'd put it up against anything that's out there today. So just to give you an idea of execution time, remember here, faster is worse. So on the original DES algorithm on my test system, 337 nanoseconds is how long it took to generate a DES, to encrypt a DES password on the mainframe. This is all mainframe. KDF AES on the default setting is an order of magnitude 10 to the 6th slower than the original DES. So already now we are at a significant speed decrease in terms of storing your data. And then just changing some of these parameters that I said don't do this yourself, just to get an interesting idea of what it looks like all the way up to the max of 3 minutes. So that last one, when I was doing this testing, it's kind of a funny story. I was testing this along the way, and you can see, for instance, the one just before the last there, 10 seconds. That means from the time that I hit enter on my password on the system, 1, 2, 3, it takes 10 seconds for the system to come back and tell me that that password was correct, because it's actually having to do that level of computation on the system. When I got to the last one and I tweaked it all the way up to the max one, I thought I'd locked up the system, and I just ended up walking away from it and coming back a few minutes later, and it had evaluated, and I realized what happened was that it actually just took almost 4 minutes to evaluate the password. Now, that's not something you would do on a system today, but you can see where as the CPU gets faster, if these defaults get bumped up, then you can make it continue to take arbitrarily longer to evaluate your passwords, which is a good thing. All right, I'm going to take a quick breath there at the end of part 1, see if anyone has any quick questions, and then we'll go on to the self-encrypting drive section, which is a little bit shorter and won't take as long, and then we'll be done. And if you want to save your questions for audible questions, we can do that. But if you have one right now, just go ahead and type it into the box. Okay, going to go on to self-encrypting drives. So part of IBM's pervasive encrypt. Yep, go ahead.
Chad, excuse me, we do have 2 questions. One is, what does SALT stand for?
Now I can see it. I had that window minimized. Yep. And what about ACF2? I see them both. Perfect.
Okay.
Okay. So what does SALT stand for? I'll take that question first. If we go back to generating, to brute forcing passwords offline, if we take a simple example, say we have a password sunrise, and we run that through an MD5 hashing algorithm. By definition of a hashing algorithm, the output from any given input will always be the same. So if I type in sunrise, pass it through MD5, doesn't matter what system on what planet I use, the output will always be the same hash. That's by definition of a hashing algorithm. So what if you're thinking ahead here, what you might realize is before salting, and we'll talk about what salting is in just a second, but before salt, what people were able to do that wanted to be able to brute force or crack your password was generate massive lists of hashes before they even got the ones off your system, and then they could just compare them. So they could take potential password candidates, Sunrise 1, Sunrise 2, etc., run them through MD5, then just save the resulted hash as well as whatever password it was that generated that hash. And now when I get your password database from Linux or whatever, I don't actually have to go through this brute forcing process. I can just compare the hashes. And those were called rainbow tables. If you Google rainbow tables, you'll get some idea of what that is. Early Windows password hashing was notoriously vulnerable to this. So I could just carry around hundreds of gigabytes of these rainbow tables, and then once I got your password list or your password hashed file off your system, I could just compare them. Now, the mainframe was never susceptible to those because it took the username into account when it encrypted data. So your encrypted data stored in the mainframe is a function of your password and your username, which is used as sort of a salt. What a salt is basically just a few random bytes that are added to whatever your password is and then run through the algorithm, and then the result is stored along with the salt. So for instance, in this same example, if my password is sunrise1, the system, when I entered it the first time, the system would generate, let's say, 3 random bytes of salt. Let's just say ABC for ease of math. And what it would do is before it hashes my password, sunrise1, it adds, or prepends or adds to the end or whatever, ABC. So the system hashes ABC sunrise1, and then in its file it stores the resultant hash and the characters ABC. The next time I come in, I type in my password, the system reads that salt, ABC, adds it to my password, runs the hash again, and then checks to see if they match. What this forces the industry to do, as the password crackers or the bad guys to do, is now you can no longer pre-compute all those hashes. You have to do each one separately because each password stored has a different salt. And so now, given that most of them store with maybe 4, 5, 6, 8 bytes of salt, it's no longer possible to pre-compute all of these hashes because you'd have to do every possible password candidate against every possible salt permutation, and you would end up with an exorbitant number of hashes that wouldn't be manageable. So that's what salt is. ACF2. I'm not going to, ACF2 and Top Secret have their own algorithms, so it's outside the scope of what we're talking about here. I'm not going to talk about ACF2 or Top Secret here. There's some documentation on CA's website that talks a little bit about how their algorithm works. And then I see there's one more password when converted to, so the question is, if I convert a user to KDF AES, can I restore their individual DES password for a specific user if necessary? So you can't get that password back, but you can change the algorithm back from KDF AES to legacy, which is DES, and then that user they can change their password and then it will store it as DES again. But there isn't a way to sort of reverse it. Once the password gets converted from being stored as DES encrypted to being stored as KDF AES encrypted, you can't go backwards. All right, good questions. Nice to know folks are listening. Thank you. All right, self-encrypting drives. Let me just click back over here. Okay. So self-encrypting drive. Basically, you may or may not know this, but if you have, we'll just talk about IBM disk and tape and virtual tape for right now, because it's what I'm most familiar with. But if you have, let's say, IBM DS8K of some reasonably new model, you may know that it has, and they market it as having data encryption built in, data encryption at rest. And it does this by using what are called self-encrypting drives. Now, you can buy self-encrypting drives at Best Buy and put them in your home PC, and some of your servers probably come with them. Self-encrypting drives basically include the encryption algorithm in the firmware of the drive. And so the encryption of the data is actually transparent to you. And a lot of people don't know that a self-encrypting drive is actually encrypting your drive always. It's encrypting your data out of the box. You say, well, okay, I'm using these drives in my array, but I've never actually set a key on these or anything, and you're telling me it's encrypted? Yeah. It's actually encrypted from, it's actually encrypting your data from the factory. But when we talk a little bit about how they work, you'll see why when you set a key, then that's actually where you get the security out of them. But they're actually encrypting as we speak. And so that happens in the firmware of the drive, which is a really important thing to understand. When these drives leave the factory, and there's only a handful of drive manufacturers now, Seagate and Western Digital, that firmware is loaded on the silicon, on the chips on that drive. There's a few, there are some APIs that can be used to access that firmware to do certain things with the self-encrypting drive, but you cannot actually retrieve, for instance, retrieve the key or read the raw data on those self-encrypting drives once they've left the firmware. Once they've left the factory, excuse me. And the other thing I'll say about self-encrypting drives is, and this is kind of the crux, and then we'll dig into why here. But the use case or the risk that's mitigated with a self-encrypting drive, and one of the reasons why I do this talk is to kind of build this awareness, because a lot of people think, when they think of data encryption at rest, what they're thinking is something that's like PCI compliant, like storing, credit card numbers, social security numbers, personally identifiable information, storing that data encrypted so that if me or Jerry or one of your system administrators, were able to dump the database and look inside your DB2 database, they wouldn't be able to read that data because it's encrypted, and that's not the case. What self-encrypting drives do is store that data encrypted on the drive, but anyone who can access that drive, which is basically your operating system, that encryption, that decryption of that data is done long before it gets to the operating system. So the only real risk, and we'll talk a little bit later about whether or not you believe this is effective, but from a marketing perspective, what those drives protect you from is the risk of a lost drive, or potentially, again, if you believe in them, so you can sell the drive to somebody else, and you don't have to worry about them being able to get your data off of it. So theft, loss of a drive, or reselling, repurposing of a drive is the only thing that this full storage array encryption, now this isn't IBM's dataset level encryption that just came out. This is self-encrypting drive encryption, which has been around for years and years and years. If you bought a storage array and they said, yeah, we encrypt your data at rest, a year ago, 2 years ago, 5 years ago, that's what we're talking about here. But they do not protect you against someone who has access to your system, so they have an ID or something like that. They do not protect you against that person, just reading a file that they have access to. So somebody asked a question here, do you need a second non-encrypted drive to boot on a PC, for instance? That's a good question. The answer is maybe. On a PC, for instance, if you have your primary disk and it's encrypted, there are two ways the system can use that disk as a boot disk without having a second disk. One is something called a TPM, which is a trusted platform module. It's a little bit of it's a chip inside your computer that stores keys, and it can provide the key to the hard drive when it powers on and decrypt it for you. And that way, if the drive ever leaves your PC, it can't be decrypted because the keys are only on your PC in that firmware, in that chip that's on your motherboard, and they cannot be extracted. The second way that you can use a drive like that on a computer is some BIOS. BIOS on PCs will support the user entering a password or passphrase when you turn it on. So not to be confused with like full disk encryption software like PointSec, Checkpoint software, but the actual BIOS will prompt you for a password, and that password will be used to unlock the drive, so maybe. Or you can have a boot disk that does that unlocking for you as well, but the other two are options that work. Good question. All right, let's go on to the next slide. So here's how a SED works, and here's why I say it's encrypted from the factory. There's two types of keys on a SED drive. There's a data encrypting key and a key encrypting key. The data encrypting key doesn't get changed, and it's set at the factory. It's not exportable. You can't get it off the drive. Interestingly, it's actually stored on the disk itself. It's actually stored on the platter in the case of a spinning drive. But you cannot get it off with any normal human means or by any research I've ever seen, ever done. And then there's a key encrypting key, or which is sometimes called the access key. This is set by the user. And so when you get a drive from the factory, the data encrypting key is always on. You can't pull it off. And so the data you write to that drive is being encrypted. It's just being decrypted transparently because you haven't set this access key or this key encrypting key. Once you do that, and for instance, your DS8000 storage array does that at the array level, so it will set this access key on all the drives. Once you do that, and then maybe store it offline in some kind of key manager like Tivoli or something like that, once you set that key, what actually happens under the scenes is that key encrypts the data encrypting key. So when you power up the drive for the first time and it gets that key from you, the access key, or from Tivoli or whatever, it unwraps the data encrypting key, and now, as long as that drive stays powered on, the data reading and writing from that system is transparent to you. As soon as the power is removed from that drive, that access key gets wiped from memory, and now in order to access that data again, you have to enter that key encrypting key or that access key again to decrypt the data encrypting key and so on. So it's sort of like an analogy I use, which is sort of like is if you've ever gone to a house, like to buy a house or sold your house, and you know the realtor puts a box on your back door that has the key to your house in it. So the key to your house, and then that little box has maybe like some buttons that you push on it that the realtor knows, and then the key comes out, and then they use that to unlock your house. So that key box, so it sort of works like that. The key to unlock your house is the data encrypting key, right? You don't have to give the realtor or all the people that are going to come see your house a copy of that key, right? That would be a nightmare. So that key goes inside the box, and then there's a code set on the box. You give out the code, people can get the key and unlock your house. Now, obviously, the analogy falls down there a little bit, but it gives you an idea of kind of how this works. The other thing to think about here, especially if you're someone who deals with cryptography at all, is the ciphertext, the actual encrypted text that's written to the disk is not retrievable. And you say, well, why would you want that anyway? One of the ways that you test a crypto system is by writing known data to the encryption algorithm and seeing what comes out and making sure that is encrypted data. Because we can't retrieve the data off the system, we don't know what's actually being written there. And here's why that's important. So I've said most of this already, so I won't read down these bullet points. But I will say is, when you talk about cryptographically sanitizing these drives, like a lot of these drives and these arrays, the vendors will say, hey, in order to sell, if you want to sell this, you just enter this command, or you push these buttons, or you run this routine, and it sanitizes and wipes all the drives. It's not actually, with some exceptions, most of the time it's not actually wiping all the drives. It's just going through and changing that data encrypting key. And once that data encrypting key on the system is changed, now remember I said you can't retrieve it, but you can change it. You can't tell it what you want it to be. You just tell the firmware to change it, and the firmware says, okay, I changed it. So once you've changed that key, it'd be the equivalent, again, back to my analogy, of changing, going into that realtor's box and putting a different house key in there, or changing all your locks, and now nobody has that key anymore. And in theory, then, no one can retrieve that data. It does meet one of the lower FIPS 140 standards. The OPAL specification is what basically talks about self-encrypting drives and how the APIs work, the reset mechanisms, authentications, all that kind of stuff. It is a very thick communications protocol, etc. But here's where it breaks down for me. So we are basically then trusting the manufacturers of these drives who write this firmware, putting it on this drive, to know that the algorithm is implemented correctly. And say, well, the contractors and the developers who actually write that code don't have access to the key. It's generated on the drive. It never leaves the drive. The manufacturer doesn't have a copy of it. Well, that's great. So I don't have to trust the key. I can change it. But what about the developer, and what about the algorithm that they're writing? How do I know with something as important as one of my drives and that data encrypted that the algorithm is actually doing what it says it's doing? It might not be. It might just be storing the data clear, or they may have put more likely, they could have actually just, poorly coded, because they're human and poor coding happens all the time, something in that algorithm and how they store the data, and now maybe it's not being stored as securely as we thought it was, and maybe somebody with the ability to take that platter out of there can reverse this, or gets the firmware and reverse engineers it. Or maybe, if you want to go real tinfoil hat on me, maybe there is a back door, right? So if you think about, and you go back even the last 4 or 5 years, loads of software, huge organizations have had problems because their software wasn't written or implemented correctly, and they've either found a vulnerability or intentional backdoors, right? Juniper, in 2015, 2016, they found a backdoor in their router software that was implemented in 2008. So this is where it broke down for me, and where I became very, very skeptical of self-encrypting drives. One, because they only protect you against the risk of them being hauled out of your data center, and two, because we can't prove that it's actually working. And for cryptography and for people that do crypto, that's really important to be able to know that it's actually doing something. Otherwise, it provides a very false sense of security. Now, having said all that, should we implement it? Maybe, right? I cannot say yes for sure and say, well, maybe it's better than nothing. Yeah, maybe it's better than nothing, but maybe not. Well, why not? Well, if you implement this encryption at the drive level, the self-encrypting drive encryption, and then as it does, word gets out, and someone comes to you as the mainframe storage people or as the mainframe crypto people and says, hey, is our data encrypted at rest? Are you going to sit and explain to them what that means and what they're really asking about, and yes or no? Or is word going to get out that you have these drive arrays, and maybe word doesn't get out internally, maybe your vendor, somebody else say, oh yeah, you've got this, you can just turn this on. But ultimately, it's going to end up on a compliance report somewhere, PCI or something like that, and someone's going to say, oh, your data's encrypted at rest. Great, give me a sample of your data, and it's like, well, this isn't encrypted data. And say, well, they said it was encrypted. Yeah, but that's at the drive level. That only protects me from a loss of a drive or potentially selling that drive. So I think as far as pervasive encryption goes, the encryption that IBM released mid-summer basically solves this problem if you use it. The data set level encryption encrypts the data as it's from the operating system level written to the drive. So it can protect you, depending on how you do your key management, from a user having access to that data. For instance, with data set level encryption, you could have a key for the application that needs to read and write the data, or the user, maybe a developer that needs to read and write the data. You can have a different key for a storage administrator who just needs to back that data up, or restore that data, or move that data around from volume to volume, and they'll be able to do that but not actually read the data. So self-encrypting drives are a little bit of a Pandora's box. If you're going to sell your drives on the open market, yeah, it's better than nothing, and I would say implement it, because as of yet, no one's ever proven that it doesn't work. But a lot of large organizations, that's not enough to just basically say, well, it hasn't happened yet, so it must be good, right? The headlines of the Wall Street journals are filled every day with companies who have been breached, and yesterday they weren't. So I would just say, proceed with caution. Have other ways of making sure that your data is irretrievable if you're selling those drives or whatever. But that is really the end of this at this point. I'll take questions now. I know we've got like another 5 minutes, but I can stay a little bit longer than that if anybody else wants to stay. So Jari, if you want to unmute everybody, and if anybody has questions, I'm happy to answer them.
All right, let's do that.
The leader has unmuted your line.
Okay, just
a reminder. Thanks everybody for staying and listening. I appreciate your time today, and yeah, if you've got questions, go ahead.
This is Jerry. Just a reminder to those of you who may have joined us late, we have recorded this session, and once we have the opportunity to edit it and upload it, I'll be sending out an email with a link to Chad's presenter page on newera-info.com, and you'll be able to access the slides and view and listen to the recording. So if you have any questions right now, they will be on the recording. Please ask.
I've got a question about encrypted drives.
Yeah.
Oh, if the encryption is built into the drive, couldn't you just pull that drive out of whatever unit it is and put in another unit and still read that data?
Yeah. So potentially the answer is yes. If the key has never been set, the access key has never been set, absolutely. You can move it around at will and read the data. If you know the access key and you move it from one system to another, you can also read the data. If you've set the access key and you don't know it, then if you take it from one system to another, that's where you're not going to be able to read the data. The firmware will stop you from reading the data unless you have the correct access key, which is the one you have to set when you initially get the drive. Otherwise, it's transparent.
Okay, that makes more sense. Okay, thanks.
Sure. There's a written question here. The experience with organizations. What's my experience with organizations that have implemented passphrases? What were the main obstacles? To tell you, the number of organizations I've seen that have implemented them, I could count on one hand. But the main obstacles are legacy applications that front end, like TSO, for instance. So just think about the normal TSO login process. You know, you've got that screen where you put your username and then your password. Well, in a passphrase, that screen changes a little bit, and that field where you type your passphrase in is obviously longer. It's got to be able to accommodate like up to 100 characters. The challenges that I've seen are not on the mainframe, but are on other applications that front end the mainframe. So you could imagine like a web app or a CICS app or something that uses a password as part of its processing, front-ending it and saying, oh, you won't change your password, or you're trying to type your new password and it's longer than 8 characters. The mainframe doesn't accept 8 characters. This is broken now, right? Instead of relying on the mainframe to do that, or maybe it's scraping the screen, etc. Those tend to be the issues. The issues are with the applications that interact with the mainframe. And you know, if you've got a shop that's been around for a while, fairly well established, the trick is how you find them and how you work through that process. It takes a diligent project in QA to go back and be able to do that. Good question. I've got another question on here. Doesn't data striping add a significant level of data obfuscation? Disconnected drive is useless if it's just a data stripe, right? Yeah, you know, that's a great question, and it's funny. I made a comment to IBM one time when we were building arrays. We had these wide stripes that went across, you know, multiple volumes, and those volumes were on different arrays, different, you know, physical arrays, and then each of those volumes maybe covered, you know, how many RAID ranks underneath, and then those RAID ranks were actually comprised of, you know, 5, 6, 7, 8 drives. So any file you write, assuming that it had a little bit of on it, you know, could be sitting on 100 drives, right? Some portion of it. Not only that, but it's CKD data. Like, you know, it's practically, the joke is it's practically encrypted already, right? But the answer isn't quite that simple, and you cannot count on that. So yes, there's some level of obfuscation there that happens with wide striping, but who's to say that you don't have some data element that is readable within some drive, or that you're not, as a bad guy, for instance, maybe in the case of selling an array or something, maybe you have enough drives to be able to put that back together, or if you're stealing it, you have enough drives to be able to put that back together on any one drive. Yeah, maybe, but it's not, you know, if you're serious about protecting data, you know, that level of obfuscation is not something that I would hang my hat on or tell an auditor about, but it certainly is, you're certainly right on. good question. Any other questions?
Okay, if we have no more questions, we'll end today's webcast. Chad, thank you very much. We can't do this without you. We truly appreciate it. We've got a comment coming in, excellent presentation. I agree. I think everybody else agrees to that. We will be sending out an email with links to the slides and the recording after I have a chance to edit and upload it, so watch for that.